All right, welcome to my channel. This is the first in a series that will be covering all the questions contained within the ASA to Fly 2021 Instrument Rating Test Prep Book. I think that this is for your money and value the best resource you can buy to prepare for the instrument rating exam, the written one. And the questions that are in this book are pretty much verbatim pulled into the actual exam, or these questions are pulled from the exam. Either way, they're almost identical. You could use this book, read through it cover to cover, and you will probably get a very high mark in the 90s. So I highly recommend purchasing the softcover book to follow along. But I've also gone ahead and scanned the pages for this video. So again, you can watch, YouTube channels, and people will be generally recommending programs such as Gleim or King, and I'm sure they're great, but all I used was this book, and I got a score in the 90s. I think it's pretty straightforward. That being said, I had kind of a tough time finding any resources that went over these questions, and that's the reason I'm making this video. So hopefully you guys will be okay with me covering concepts and trying to relate these diagrams and figures to real life instead of just going over questions. Because in addition to the questions, there are also explanations as to why some of the answers are wrong. And some of that requires more reading and research. So hopefully we'll be able to cover all of that, and you guys will have some patience with me, because this is actually my first video. So without further ado, let's cover the first page, which is about weather, specifically about the Earth's atmosphere. So you can see in this diagram that the Earth's atmosphere is split up, excuse me, guys, into a number of layers. And the ones that pilots are most concerned with are the troposphere and the stratosphere. The mesosphere, probably more relevant to astronauts. So you can see that the shapes here are a bit different, and we'll get into why that is. But first, I want to focus on what kind of identifies these layers. Why they're separated, what's a good way to think about each one of them, how to kind of identify them. So let's talk about the troposphere. Um, I'll get into the kind of height later, but some of the key features of the troposphere can be explained by looking at mountains. So if we look at the tallest mountain, or I should say the highest elevated mountain, the tallest mountain is actually in Hawaii, but Mount Everest is the mountain which reaches the tallest elevation, which is 29,000 feet. So you can think of it as 30,000 feet. And it sits right on the border of Nepal and China, or Tibet. A key trait of the troposphere relates to how it becomes more difficult to breathe as you climb up altitude. So if you've ever seen those movies about people climbing Mount Everest where they have kind of oxygen masks with them or oxygen tanks, or if you've ever climbed or have visited, let's say, a high altitude area, for example, Colorado and New Mexico, you might have experienced altitude sickness because there's less oxygen going to your brain. But regardless, it's kind of intuitive that the higher you climb, the harder it is to breathe. So, you can assume that at a certain point, if you climb far enough, you won't find any oxygen. And that's a good way to think about the troposphere. The troposphere, for all intents and purposes, contains all of the oxygen in the atmosphere. Now, that's not entirely true because it only contains 99% of oxygen, but to just get through these concepts, it's a good way to think about it. The boundary you could think of the troposphere, which is the tropopause, this little line here, the border. The tropopause you could think of as containing all of Earth's oxygen. So if you went beyond the troposphere into the stratosphere, there would be no oxygen. Again, that's not entirely true, but just to get through these concepts, that's a good way to think of it. Another key characteristic of the troposphere can be related back to the same uh, mountain climbing experience, right? So if you've ever seen Mount Everest videos, you'll notice how there's always snow at the top. Actually, even here you can see all of this white is snow. This picture, generally speaking, if you've ever climbed to a higher altitude, it just gets colder, and you intuitively know that the higher you climb, the colder it gets. And that is indicative of the entire troposphere. So if you continue to climb up from the ground, from Earth, up until the tropopause, up until that border that covers the entire troposphere, it'll just keep getting colder and colder as you climb up. Now, those two characteristics really reflect the troposphere, and they're the most important aspects to understand. Those two concepts, that the higher you climb, the less oxygen there is, and the colder it gets. All right, so this is where things kind of get interesting because once you break through the tropopause and you're into the stratosphere, the higher you climb in the stratosphere, you experience the opposite effect of what happens in the troposphere, in that temperature actually rises. So the closer you're getting to the sun, the warmer it's getting in the stratosphere. And it's kind of easier to think about it when you draw a picture. And I actually recommend anybody following along also try to illustrate what's going on here. So let's look at it from the first angle of, we can draw the sun here, right? And then we can draw kind of the Earth. Let's draw the Earth here. I should make that blue actually. Let's make that blue. And then we can draw some extra layers here. We can draw the troposphere. Let's move that a little bit. And we can draw the stratosphere. So, all right, we got our two layers here. Now, the way that we get warmth into Earth is through sun rays. I mean, it's pretty elementary. It's something that everybody kind of knows. We've got sun rays hitting. Oh, still drawing circles here, sorry. We've got sun rays kind of going in, right? Well, it turns out that there are actually three types of rays. We've got, let's draw a little bit of a thicker one. We've got our short rays, which are the UVC rays. Okay. Not sure why that's a different color. So we've got UVC, and that just means ultraviolet C category. So we can put a box on that. And we've got our medium range ones, which actually break through the tropopause here. Okay, so the UVC rays, they get actually filtered out by the stratosphere. The stratosphere contains something called the ozone layer, which is just O3. So you can think of oxygen as O2, and the stratosphere contains something called a layer. It's an ozone layer, which is made up of O3. Now, the way O3 elements are created is basically you have two O2s, and what happens is the UVC ray breaks these two apart, so you get O here and O here, and they automatically like to get back into another element. So that's how you get kind of the ozone, right? Now, the ozone is really good at absorbing UVC rays. These short rays, they just get kind of bounced back. They get canceled out here. The medium range ones, the UVBs, right, ultraviolet B rays, they are able to break through the ozone layer, and they're actually generally just kind of breaking through into the troposphere, and they never really reach the Earth, right? For the sun to reach the Earth, that gets carried through the UVA rays. So we got long range rays here, and they actually touch the ground here. So these are the longest ones. These are UVA, okay, long range ultraviolet rays. So these two here are able to pass through the ozone layer. And UVB is actually what generally most people can associate with skin cancer. Okay. These are the most harmful rays that generally break through into the troposphere. So these are harmful. Okay. Now the UVAs, they're really good for us because they give us warmth. We got a little radiation here. They are what allows, plants to grow and photosynthesis to happen. So UVA, good, UVB, bad. Now you might be thinking to yourself, what does all this have to do with the change in temperature at the stratosphere versus the troposphere? Because remember, we mentioned that as you go up in the troposphere, the temperature drops, so it gets colder. And as you move up in the stratosphere, it actually has the opposite effect. It becomes warmer. Well, that all goes back to this ozone layer here. This layer is pretty close to the tropopause. It's around here, let's call it. And so what happens is, despite the rays filtering through here, right? Some of these getting caught up in here, not passing through, others passing through. As you move up, you're actually getting closer to the sun, right? And so what happens is you're basically getting the effect of these short rays. So these short wavelength rays, they're much warmer, right? So the closer you are to the sun, it's just going to get hotter because the rays are much shorter. And that explains why once you move past the tropopause and you're kind of at this ozone layer, right, it gets warmer here because all of that heat is being absorbed from the rays that are being filtered. And then as you move past that point, the rays, the UVC rays, and actually the UVB and UVA rays, they're all kind of coming through here, but they're at a much shorter distance from the sun. And so it's going to be much warmer as you move up, right? So it's going to be warmer. Let's say, let me draw that with this pen here. So you're going to be warmer. Okay. Now, at the troposphere level, there's going to be an opposite effect where you're going to get colder as you move up because that heat that was brought in from the UVA ray, right, which is radiating, well, it's only radiating near the surface of the Earth. So you get that warmth here. It's going to be nice and toasty. And then you got the UVB rays here, but they're not being absorbed by really anything. So what happens is you've got this heat and you start losing that as you move up. And it's only once you break through the tropopause where you start feeling the warmth again. Now we can look at it from another angle here, and that'll kind of paint a better picture. So let's draw the Earth's ground here. All right, this is the planet. We can draw a troposphere here and a stratosphere. Now, you've got the sun here, so we'll do like a zoomed in version. Okay, so, and you've got, let's say, oh, we've got the UVA rays that go all the way down. I think we used a different color for those, so we can use this orange. So we've got the UVA rays, UVA, and they get absorbed by the ground, by the ocean. The ocean is a really good absorber of heat. And so what happens is you've got a little bit of a radiating heat coming out of the ground here, out of the water, and that's close to the Earth. So it's nice and toasty here. Let me draw a little bit of toast here. Okay. Now, you also got UVA rays that bounce back, right? Off the ground. So you get kind of also some warmth here, right? It's going to be nice and toasty here, and it's going to be warm here, right? So it's getting colder as you move up, colder. Now, if we get back to the ozone layer in the stratosphere, got this ozone layer, and it's absorbing all of those UVC rays. We've got UVC here coming in here, right? UVC. And what's happening is the closer you get to the sun, right? The closer, the shorter those UVC rays are. So as you move up, this is going to be more intense than this, right? Okay. So as you move up, it gets actually warmer. So the opposite effect of the troposphere. Now, so far, I've been kind of drawing the troposphere as an even base. You can see here that it's pretty straight here. Even in the last picture, I had kind of the troposphere as a round shape. But as you can see in this diagram, the troposphere actually is a bit expanded at the equator. It's actually almost a bit over 2 times taller or at a higher elevation than it is at the poles at the equator, right? So a good way to kind of understand why that is to think about what is contained in this troposphere. So again, we said the two characteristics of the troposphere are one, that as you kind of climb up, you run out of oxygen, and the other being that as you climb up, it gets colder. Well, it turns out that oxygen likes to expand with heat. Okay, we'll go over kind of all of that later because there are many more questions in this book that touch on that concept. But for now, I just kind of want to work off of that idea that as you warm air up, and you can actually think of a hot air balloon, as you kind of warm air up, it likes to expand. So let's try to kind of draw this. All right, that's going to take a little while here. We can draw a hot air balloon, and you know that as you kind of warm that air up, right? You've got, let's see, a little fire going on here, right? Well, that air likes to kind of expand. It likes to move up. So the question is, that looks like kind of a weird eyeball, but the question is, why does it seem that the air in the troposphere is expanding at the equator? Well, that just happens to be the warmest part of the planet. And we can actually visualize that by relating how the world is kind of placed near the sun. So if we draw a crude sun here, we can kind of draw it in the middle here, and we draw the Earth. We can draw it here, we can draw it here, it doesn't really matter. Let's draw it here. So one of the things that is important to understand here is that there are diagrams that show the Earth as kind of face straight up, but in actuality, the Earth is tilted, right? So I just want to draw this. We might as well take care of two birds with one stone here. So let's draw the line for the tilt. So you got a tilt going on here, right? And this is actually where the North Pole is. This is the south. Okay. And these two are divided by an equator, right? I'm going to draw that equator here, divides it into the northern hemisphere and the southern hemisphere. Now, if you notice, the closest point to the sun is going to be right here, right below the equator. Let's draw a line. Sorry about that, guys. So the closest points are going to be right there, and then it just kind of gets a little bit bigger. That's the equator it's touching, and you can see that these lines are around the equator. They're much shorter than the lines that hit the poles. So we got, it's kind of not straight. Got a line here. You can tell that these lines are much shorter. Well, if you brought a ruler in, you would see that this line is going to be shorter than this line. But the Earth, as it happens, actually spins, right? It spins counterclockwise. It also revolves around the sun counterclockwise if you look at it with the North Pole up here. So since it kind of spins, right, in a day, that means that in one day, this part right here of the equator would go around. After 12 hours, it would touch on here, and then it would get back, right? So that means that for 12 hours, it's moving from here to here. And so is this whole part right here underneath. It's moving, and then it's coming back into here. So what you get, actually, is that this whole area here, right, is going to be warmer. The entire part under the equator. But if you look at how the Earth revolves around the sun, on average, what's going to happen, let's draw another Earth here. I'm going to draw the Earth. I'm going to draw a tilt here. Oh. Sorry guys, bear with me. And you have the equator, right? So you got your north and your south. All right. Now, what happens here is the exact opposite effect, right? You have it coming right onto the Earth here. And so the shorter area, the warmer area is going to be right above the equator. Well, that just means that on average, the equator is going to be the warmest spot, right? You have it being half of the year right above it, half of the year being right below it, and obviously in between here, it's going to kind of get closer, right? So that just means that the equator is the warmest spot. And that's because the rays that touch the Earth, that touch it at the equator, are going to be the shortest distance to the sun. So they're going to be the warmest. Now, another key important aspect, which is shown in this diagram, is that it's actually summertime on this side in the southern hemisphere because this uh, ray that's touching on the South Pole is actually shorter than the ray that's touching on the North Pole. And that's because of the tilt, right? So all of these rays right here, let me see if I can get a darker color here. All of these rays are going to be shorter. So that makes this entire part of the circle warmer. And that's what gives us summer in the southern hemisphere on this side, summer. Sorry, guys. And on the opposite end, summer over here. All right. Not very pretty, but this kind of explains why at the troposphere, the air expands near the equator because it's just warmer there around the entire year, right? You're going to have it expand here at the equator because it's just warmer. So the key element here is the heat from the sun reacting with the oxygen. Now, at the poles, right here at the North Pole or the South Pole, it's still going to be colder than near the equator, right? So the distance between the sun and the North Pole and the distance between the sun and the South Pole is not going to be a great difference, right? So it might be a little bit closer to the South Pole, but it's still, not a big difference, not as big of a difference as something from the equator is to the South Pole, right? So the South Pole is going to be almost as cold as the North Pole if you look at an average. And for that reason, especially since as the Earth is revolving, right, as it's kind of becoming winter here, on average, the poles are the same. Just as on average, anything right below the equator and right above the equator is going to bring the heat all into the equator. On average, the poles are going to be just as cold, right? They're both equally as cold on average. So the oxygen, the air, it likes to sink, right? It's instead of expanding, right? I'm drawing this on the sun for some reason, but so if we got the north here, we got the south, the air likes to kind of sink instead of expand. It has the opposite effect, right? Because, for example, if you try to boil something, okay, it's going to evaporate, right? It's going to rise. But if you didn't do that, it would kind of still stay below here. So that's the effect that temperature has on oxygen. And that's the reason why the troposphere is shaped this way. So I think we have enough information to kind of tackle the first question, which is 4097. A characteristic of the stratosphere is an overall decrease of temperature with an increase in altitude. Well, we know that's not the characteristic of the stratosphere. That's actually the characteristic of the troposphere, right? Because as you move up in elevation in the troposphere. You're getting away from that radiation at the Earth, and so it's getting colder, right? Overall decrease of temperature. Now, answer B says that there's a relatively even base, okay, at the altitude of approximately 35,000 feet. The thing is that the base of the stratosphere is also the top of the troposphere, right? They're both the tropopause. Now, what we've just kind of went over here, which is how the heat from the sun affects the oxygen in the troposphere, we know that the base is not going to be even. We know that it's going to be more expanded, greater elevation at the equator for the troposphere. And we're going to go over kind of how to think about what height, but we know that it's not an even base, so we don't even have to think about 35,000 feet here, which we'll get back to on the second question. So that leaves us with C, which is relatively small changes in temperature with an increase in altitude. And that's true because as you're moving away from the troposphere into the stratosphere, there is less of a difference, okay, in the rays, right? So let's see if we can get back to this one. So the difference in heat here, okay, at the Earth's surface versus the tropopause is going to be greater. There's going to be a greater temperature difference than there is at the tropopause and the stratosphere. Or the end of the stratosphere, the stratopause. The difference is because all of that heat is being absorbed here creates basically a greater variance, right? There's much more heat here. Let's make a little fire here. And the warmth in the stratosphere, while it does get warmer, the difference is not as great as it is at the tropopause, or at the tropopause versus the surface. So again, relatively small changes in temperature with an increase in altitude, but we know that it's getting warmer. Okay, and we can see here answer A is incorrect because temperature increases with an increase in altitude, right? So that, again, we know that it gets warmer. So that leaves us with answer C. I think we'll just do one more here because the question after that is going to take a little bit more of a deeper dive into other concepts. So let's look at 4154. The average height of the troposphere in the middle latitudes is, and in the beginning of this video, I mentioned that I'm going to try to kind of stay clear from trying to memorize figures and diagrams, but sometimes you do have to kind of just remember some numbers to get the answer right. And a good way to do that is kind of associate it with some reference points, some kind of things that you're familiar with. So the first thing I think I'll do here is try to define what a middle latitude is. And I think just an easy way of doing that is, first of all, let's define what a latitudinal line is, right? We got longitude and latitude, and the way I like to look at it is kind of like a ladder. So you got a bunch of sticks here, for lack of a better word. So these long ones, long, you can think of as longitudinal, longitude. And these short ones that make up the ladder sounds like latitude, right? So we got latitude. All right, so mid-latitude just means in the middle. We have the Earth here, we have the equator. You know what? Let's get a real picture here. All right, we got Mount Everest here, and that'll be our reference point actually. So let's get the entire Earth here. Let's make it so that the equator is straight. We have Mount Everest here, and we can just copy this over. Let's make a new one here. Oh, pressing every possible button. All right. So again, we got longitudinal line here we can draw, right? And the equator is just a latitude, right? It's latitude 0, actually. So we can say latitude equals 0 degrees. This is longitude, okay? And we'll go over kind of the Greenwich line later, but just think of this as a random longitudinal line. So right in the middle here, a mid-latitude would actually be exactly where Mount Everest is, which is what makes it such a great reference point. So we got Mount Everest here, right on the mid-latitude. Now, if you remember, the height of Mount Everest was 29,000 feet above sea level, right? So almost 30,000. Make that a little bit bigger. So 30,000 feet. All right. The way I like to think of it is, instead of trying to memorize what that is, I just like to think of the equatorial line as being the equivalent of 2 Mount Everests, right? We got 1 Mount Everest here. The equatorial line being 2 Mount Everests would be around 30,000 feet times 2, 60,000 feet, okay? And you would just have to remember we got the North Pole at around 20,000 feet. Okay, so the average would be around 40. All right, it's kind of a long way around it, but that's how it works for me to memorize. So the average height of the troposphere in the middle latitudes is, and actually, if you think of Mount Everest, right, you know that Mount Everest is going to be over 20,000 feet. You know it's going to be over 25,000 feet. You know that it's going to be in the middle latitude. So 37,000 feet makes sense because if you're on Mount Everest, the air is still going to contain oxygen at 25,000 feet, right? That's the key here because the troposphere is just kind of, you can think of it as the boundary of where oxygen runs out. So if you were on Mount Everest, which is in the middle latitude, you would still have oxygen, even though people wear masks or oxygen tanks they bring with them. You would still have oxygen at 20,000 feet and at 25,000 feet. But at 37,000 feet, that's where you would probably run out. So we got the troposphere here looking like a mushroom, right? Not a great drawing, but this is kind of, let's do it like this. Yeah. All right, so hopefully that kind of cleared some things up, and hopefully I'll see you guys in the next video. I am trying to not drag these on for too long, so I'm gonna hopefully get better at this and, you know, eventually get shorter, but kind of keep the detail and bring enough understanding into the concepts so that you don't have to just memorize these answers, but actually understand the concepts. Because ultimately, passing the written exam is pretty simple, but when you do your check ride, the instructor, the person giving you the check ride can pretty much ask any question he wants, right? And he'll look at the questions that you were weak on in the written exam and probably look at those during the check ride. So thanks for taking the time. See you on the next video.